Welcome to the Explainer. Today, we're going to demystify a skill that is absolutely critical in manufacturing, assembly line balancing. Let's jump right in. And that's a serious question, right? Because hidden inefficiencies, these tiny delays and mismatched workloads, well, they can quietly drain your resources. Today, we're going to learn exactly how to find and fix those hidden costs. When you first look at a production flow like this, it can seem like pure chaos. You've got some operators totally buried in work, while others are just standing around waiting. This right here is the classic sign of an unbalanced line. Our job is to take this tangled mess and turn it into a smooth, rhythmic, and, most importantly, profitable process. So here's our game plan. First, we'll dig into the problem itself. Then, we'll do the core math to figure out our pace. After that, we get to the fun part, solving the puzzle of assigning the tasks. Then we'll grade our own solution, and finally, we'll look at what to do when reality gets a little more complicated. Okay, so let's get right to it. Let's formally define what we're up against. What is actually happening when a line is out of balance? An unbalanced line is really just a recipe for failure. You end up with these bottlenecks where work just piles up at one station, grinding the whole line to a crawl. But at the exact same time, you have other stations just sitting idle, and that's wasted labor, wasted capacity. All of this leads to completely unpredictable output, and, of course, skyrocketing costs. It's basically a system that's at war with itself. Before we can even think about arranging tasks, we need to understand the fundamental rhythm of our production. We have to calculate the speed limit for our entire assembly line. And that speed limit has a name: takt time. Now, this is absolutely crucial. Takt time is not how fast you can work, it's how fast you must work to keep up with your customer demand. You can think of it as the pulse, the heartbeat, that syncs your entire operation with the market. The formula itself is pretty simple. You just take your available working time and you divide it by the customer demand. So for our example, let's imagine we have a standard 8-hour shift, that's 480 minutes, and our daily sales target is 500 units. So you do the math, and that gives us a takt time of 57.6 seconds. This number, this is our golden rule. It is the absolute maximum time that any single workstation can spend on one unit. If any station takes longer than this, we will not hit our target. Period. It is our line's speed limit. Okay, so if that's our speed limit, how many workstations do we actually need? Well, first we add up the total time for all of our individual tasks, all the little pieces of work. In this case, it comes out to 252 seconds. Then we divide that total work time by our takt time of 57.6 seconds. The result? 4.375. Now, obviously, you can't have a fraction of a workstation, so we always round up. That means our theoretical minimum, our perfect world target, is 5 stations. All right, now for the main event. We have our speed limit, 57.6 seconds. We have our target, 5 stations. It is time to solve the puzzle. How do we assign all 12 of our tasks to those 5 stations without breaking any of the rules? Every good puzzle has rules, and ours are simple, but they are strict. Rule number 1. The total time for tasks at any one station cannot go over our talk time of 57.6 seconds. Rule number 2, we have to obey precedence. For example, task B cannot start until task A is finished. Now to solve this, we'll use a common heuristic, which is really just a fancy word for a problem-solving shortcut or a rule of thumb. For this explainer, our rule is going to be, when we have a choice, always assign the longest available task that fits. It's important to note there are other rules out there, and picking a different one can give you a different answer. All right, let's do this. Station 1. Right now, the only task we can even consider is A because it doesn't depend on anything else, so we assign it. It takes 15 seconds, leaving us with 42.6 seconds of our takt time. Now that A is done, task B is unlocked. It's 23 seconds. Does it fit? Yep, so we assign it. Now we're down to 19.6 seconds left. Okay, with A and B done, tasks C, D, and E are all eligible to be assigned. But wait, task D takes 42 seconds. That's way too long. It won't fit. So our choice is between C and E. Following our longest task rule, we pick C, which is 17 seconds. That brings our station total to 55 seconds. We only have 2.6 seconds left, so we can't fit anything else. Station 1 is done. Let's move on to Station 2. The tasks we didn't assign last time, D and E, are our candidates. Again, using our longest task rule, we pick D first. It's 42 seconds. That leaves us with 15.6 seconds to play with. Task E is 15 seconds. That fits perfectly. Let's add it. That brings the station's total time to 57 seconds, leaving just zero point 0.6 seconds of idle time. That's a really efficient station. And with that, Station 2 is complete. And you see the pattern here, right? We just keep applying that exact same logic over and over. Find the eligible tasks, pick the longest one that fits in the remaining time, and repeat until the station is full. Following this simple process, we methodically fill out stations 3, 4, and 5. And this just perfectly shows how a logical, step-by-step process can bring complete order to that initial chaos. We've done it. All 12 tasks are successfully assigned to our 5 stations. And this is the payoff. We've taken that abstract table of numbers and turned it into a physical workflow on the factory floor. You can see our 5 stations right here, each with its own total cycle time. And notice, none of them break our 57.6-second takt time rule. Station 2, at 57 seconds, is our slowest station. That makes it the bottleneck, and it sets the pace for the entire line. So we did it. We created a balanced line. But how good is our solution really? Is it a C+? Is it an A? It's time to grade our work by calculating the line's efficiency. So how do we get this number? Well, we calculate efficiency by taking the total task time, that 252 seconds of actual work, and we divide it by the total time we've made available. That's our 5 workstations, multiplied by our takt time of 57.6 seconds. And the result is 87.5%. What this really means is that 87.5% of the time, our operators are actively working, and 12.5% is unavoidable idle time that's just built into the system. For a first pass, that is a very, very solid result. Now, what we just did gives us this fantastic, clean solution on paper. But as we don't know, the real world is, well, it's messy. So what happens when we need to account for all that real-world chaos? And this is a really important point from simulation expert Brian Harrington. He says, our spreadsheet math is powerful, but it's deterministic. That means it assumes everything runs perfectly the exact same way every single time. It's an approximation. But what about random machine breakdowns, or just normal human variation? And that's where a tool like simulation becomes an absolute game changer. On the left is the solution we just built using our longest task rule. But on the right is another perfectly valid way to group the tasks. Maybe it was made with a different rule. So which one is actually better in the real world? By modeling these in a simulation, we can run an entire week's worth of virtual production in just a few seconds and see which one truly produces more. It lets us run what-if scenarios that are basically impossible with a calculator. Think about all the chaos that spreadsheets just can't handle. Random downtime, operators who sometimes take a few seconds longer, people who have to walk between stations, changing product mixes, setup times. A good simulation can incorporate all of this random, real-world behavior to give you a much more realistic picture of how your line will actually perform. So what's the big takeaway here? We've created a balanced, efficient line based on today's numbers and today's rules. But what happens tomorrow when customer demand suddenly changes, or a new product gets introduced, or a machine gets an upgrade? The balancing act, it never truly ends. And having the right tools to adapt quickly is what separates the good from the truly great.